Hello.
Great. I'm recording the session, so I will also post this if you want. I know a few students cannot join, so they requested me to record it.
Oh.
Okay, so we are on time now, so might as well get started. So the logistics. So Thursday, of course, we will have our midterm. The logistics of the exam is. Let me. A couple more people. Let's give them a minute. Okay, I think most everyone's here. Okay, great. So Thursday we'll have Thursday, of course, we don't have a class on Zoom. That's the first thing. So I need to join. The second point is that it'll be the exam. So we will post the exam, I think, on Thursday early morning. So you can check, and it'll be posted on Canvas, most likely just as an announcement. And the exam will be a PDF, and you will have 24 hours. So it'll be due on Friday morning at the same time that I posted. So don't be late. And you can, of course, do it by hand on a piece of paper and take a picture of it and post it send it on Canvas, or email it or send it on Slack, whatever you want, but just make sure you get it to us, either me or Apratim.
Where can we find the exam?
On Canvas. It's not there yet, but Thursday morning.
Okay, cool, thanks.
Yeah, probably by 9 o'clock or so, let's say. Yeah, and if you have trouble, if you don't have it by 9, make sure you message me on Slack. That'll be the quickest, or email me.
Oh,
it should be there.
So you would post it like before class time, like latest.
Yeah.
Okay, cool. Thanks.
Right. What I mean is that we won't have class on Thursday. You're gonna get a break, but you're supposed to do the exam. So we'll post the questions probably by 9 a.m. or so Thursday, and you'll have 24 hours to finish it and submit it back by Friday 9 a.m. or so.
Okay, cool. Thank you.
And to submit it, again, I haven't used Canvas for this before, but I would say if you have any trouble, just email it. Take a picture of what you did, or scan it, whatever you want, and just email it if you have any trouble. Or you can just even send it to me on Slack, or on Canvas, whatever works. And of course, the Section 90 students don't have to do it, but you're welcome to do it, of course. Okay, I think that's basically it. Any questions on the logistics? Don't be late. If you're late, of course, we will have to penalize you. So you have 24 hours. And don't collaborate. This has to be your own work. If we find that you're plagiarizing, then that will be severely penalized as well.
Did you say it's like open book, open MATLAB, and also open internet?
Yes. Open everything. Yeah.
Okay.
And just a few quick comments. We're not going to ask you to derive anything, because that you can just look it up, right? So that's obviously we're not going to ask you, and we're not going to ask you to run some software on console or light tools or code file. That is not part of the exam. Let's see what else. Oh, make sure you show your steps. So even if your final answer is wrong, we can give you points if you show the way you're trying to solve the problem. So that's actually more important than the final answer, because if you simply write down the final answer, I'll assume you copied it from someone else. So don't do that. Let's see, what else should I say? Make sure if you write it in your hands, make sure it's legible that we can read it, right? Anything else up with them I'm missing?
Just one question here real quick. So you're
sure,
saying
go ahead.
It's acceptable to send it to you by Slack or email, right?
Yeah. Anyway, just get it to me. Yeah.
Okay. Thank you.
Yeah, Slack is great for these kinds of things. You can attach a file. Email is perfect. Canvas is fine. Whatever works for you. Yeah. And if you have any trouble, of course, just email or message me on Slack. Okay, let's see. Yeah, I think that's about it. I mean, again, the purpose of this exam is simply to make sure that you're able to understand the concepts, as opposed to, this is not a math class, it's not a calculus class, right? So we're not going to ask you to derive anything. It's more important to gain intuition and do a lot of the examples. And the goal today is to actually cover a lot of those examples. Okay, Apratham, did I miss anything?
No, I think that's it. I think mostly the questions should be similar to the sample problems, I guess.
Yeah, yeah. So it's really for your sake to make sure that you have a fairly solid understanding of what we have covered so far. And this is kind of the halfway through the semester. So the next half of the semester, really, we're looking at a bit broader, bigger picture things. So this is a good place to, kind of take a break and review what we understand so far. Okay, with that, I'm going to hand it over to Apratham. So I think you can share your screen, Apratham, if you want. I'll monitor the chat, but I might go. I might not stay at my desk the whole time.
Okay, you can see my screen.
Yes.
Right. Okay. Okay, so for the midterm review, I think I would go over some of the basic concepts that we discussed in the class, and also the sample problems and their solutions. I think maybe that should be helpful. So I posted some of the steps for one of the sample problems. I got a few questions from. Those were posted today. And I was a bit delayed getting to that, but if you have any more questions, let me know throughout this class today. Okay. So basically, just I would say concentrate a lot on the geometric optics class, because that's where a lot of the math problems are with the matrix formulations and stuff like that. So you will definitely get one or two questions that will come from this geometric optics section, right? And some basic, maybe some short questions where you have to solve some problems using these basic properties of lights related equations and stuff like that, like similar to these questions which are in problem set 2, where you're asked to find the luminous flux of an LED and so on. Right, so just remember, I'll just go over some of the more important concepts. So remember what a ray is. It's the geometric approximation of when light wave travels from one point to the other. And rays traveling follow, when they interact with media, they follow the laws of reflection and refraction. And I'm just going to go over these pretty quickly. So if you have any specific questions where you think you didn't understand something or you have something to ask, just stop me and shout out your questions and we can take a discussion from there. We use ray tracing to analyze lenses and optical systems, right? So mostly all optical systems are composed of light rays traveling from one point called the object or the source to another point, where all the rays are captured by the imaging system and brought to a focus at the other side, basically where the image forms. They're collected to the image, which is a very good representation of what the object is. And all the different, when it goes from the object to the image, remember that there's just two phenomena that we have to take care of. One is free space propagation and one is refraction. That free space propagation might be inside air or inside the medium of the optical system. And the refraction is usually at the interface between these two media. And these two are the only two phenomena which are repeated different number of times. So when the light rays go from the source to the image, the object to the image. And all the problems are being solved, in the Paraxial approximation. So remember the geometric identities that come from the trigonometric identities that come from the Paraxial approximation, which is defined by saying that the angle subtended by the rays with the optical axis is very small. And the matrix formulation is a very useful tool that we can use to analyze these kind of systems. And I derived in class how these matrices are formed. So for your midterm, this slide would be pretty important, where there are the summaries of the translation through uniform medium, or otherwise free space propagation through uniform medium matrix, and the refraction by spherical surface, or refraction at the interface of two medium, the matrix over here. So I definitely refer to this slide for sure. Also remember that you should also not forget the sign conventions. So that slide is pretty important as well. And then we looked at a few of these examples, like what happens when you have just a thin lens, which means that we are just considering the refraction at these two spherical interfaces before the ray goes into the lens and exactly when it comes out of the lens. We looked at that example, and in order to solve this problem, what we did was we just plugged in the refraction at spherical surface matrix for the two cases and solved the problem like that. So actually, I think this would be a good time for me to go over the sample problems that were posted and how you would solve them, or if you have any questions, just ask. So
I'm so sorry to interrupt you. I have one quick question here. I was studying. Okay, when you go to the matrix formulation of refraction, right? So there is a matrix formulation, for example. And let's say we're talking about a convex versus a concave lens. Would that be different, or would that be the same?
Sorry, would that be different or that be the same? That's the question, right?
Yes.
So I would say that irrespective of whether the surface is convex or concave, treat this matrix as it holds true for all cases. Okay. As in this n prime, this is output side refractive index, or n out, minus n input side refractive index, n in over r. Now, whether the surface is concave or convex will give you an additional sign to the radius of curvature.
Yeah, so that
remember the sign convention. So the matrix will hold. You just have to you write the matrix and then look up the sign convention, figure out what kind of surface it is, which way the rays are traveling, and appropriately use the sign for the radius of curvature there.
Perfect. Right? Thank you very much.
Yep. So the first question for the sample problems set 1 was, it asks the case for refraction through spherical surface is shown below with relevant equations. So this is the general case for the refraction at interface of two media, and the surface is like it's spherical here. So the normal is defined as the normal through the tangent of the circular plane, which becomes the radius of the circular surface, right? So the radius is normal to the tangent. So is it possible to alter this surface in any way to arrive at Snell's law of refraction? So just to remind ourselves, Snell's law of refraction was when a light ray goes from one medium to the other medium, and this is the interface between the two medium. How do we go from this surface or this situation to this situation? So this is pretty straightforward. The surface is circular in this case, and for Snell's law, which is a special case of this general situation, the interface is plane, it's straight. So it's simply that you make the radius of curvature go to infinity, and then if you simply replace that here, you'll see that if you solve this equation, you get Snell's law under Paraxial approximation. So remember, we get n prime alpha prime, and because this is Paraxial approximation, alpha prime equals the sine of alpha equals alpha prime, sine of alpha prime equals alpha prime, and sine of alpha equals alpha. So this is Snell's law in Paraxial approximation. I think this is pretty straightforward, right? If you have any questions on the first problem, otherwise I'll go to the second problem. Okay. So the second problem is more like maybe some problem that you will face in the midterm. So it utilizes all the different aspects which are related to the matrix formations and how you can solve an imaging system problem. So this asks, there's this goldfish which is situated inside the spherical water bubble sort of thing, and there's this person who is looking at the fish. So the first question which is, and there are these radius of curvature of the sphere, water sphere is defined, the refractive index of the water sphere is defined, and so on, and the distance of the person from this edge and all that. So the first question asked is, how does the fish look to the person? That is, where is the fish's image formed? What is the magnification? Is the image real or virtual? All these things. So this is the basic solution mathematically, and these would be the steps that I would follow to solve this problem. So this is the definition of the problem, and this is the first part, right? So what are the steps we have to take to solve this problem? First, I would identify what the input or the source is, or the object is. So in this case, it asks, how does the fish look to the person? So the fish is the input or the source or object in this case. And to the person, that means the person is the output side. That means the light rays are traveling from right to left. Now remember, this is opposite to the convention that we followed for all the other examples in class, whereas the object or the source is located to the left of the imaging system and light is traveling from left to right. So this is the opposite case. We are doing from right to left. So once I've identified all these, the input and the output and so on, I will write my matrix formulation. So how do I write that? The output side matrix equals a bunch of different matrices times the input side matrix. I'll write that down. And then what are these different matrices that I have to write? Remember, when solving this problem, we have to go from output side to the input side. That is why it's very important to first identify which is the object or the source or the input, and which is the output or the image. And I would mark those two. And sorry.
Just wondering, so where can we find the sample exam? The sample exam.
I think it's already posted today in, I think, on Canvas. Dr. Menon already posted it.
Actually, it's posted on the class website.
Oh.
So if you go to the it's on the top of the announcements, the very first one.
Okay, thanks.
So this, yeah, so in order to solve the problem, remember, we have to write the matrices going from the output side to the input side. And that's why it's very important to identify which is the input and which is the output, and not to forget while arranging the matrices in order. So going from output side to input side, I first see that there is this free space propagation. Then there is refraction at the interface between this water sphere and air. And before that, there is again free space propagation inside the water sphere. So I'll first write free space propagation in air over a distance of s. Then I'll write the matrix for the refraction at the spherical interface, at the spherical surface between the water sphere and the air. And before that, we have free space propagation inside air again over a distance equals to s prime, which also happens to equal the radius of curvature of the sphere. And again, obviously, you have times your input matrix. So that's that. This is how I would first generally formulate the matrix. So if you get up till here without making any of those mistakes, half of the work is done, I'd say. And then I would replace the values of n out and n in by the given refractive index values. So here n out equals 1 because it's air, and n in equals n, which is the refractive index of the water sphere. So I replace these here. N out equals 1, so that's here, and then n in equals n. That's all I've done. Obviously, if you're given numerical values, like if n equals 1.4, 1.2, or so on, you can replace those here. But I usually do all the numerical substitutions at the very end. But before that, I just use these alphabets to solve the problem. So now I've written that equation over here, and I will then go to this slide, which summarizes the matrix formulations, and look at the translation through uniform medium matrix and the refraction by spherical surface matrix. So I write them here again: free space propagation matrix and refraction at spherical surface matrix. They're general forms, so that I don't make a mistake. And then I just substitute the forms into this big equation, right? So free space propagation in air, I follow this form. So 1, 0, and it's d over n, which is the distance. In this case, it's s. So it's s in air. So n equals 1. So s over 1 and 1. Then refraction at spherical surface is 1, 0, and 1 is 1, 0, and 1. And this is the question that Kaina was asking. So I maintain the same form of the M12 term. So it's minus n out. Again, n out in this case is air. So that's 1 minus n in, which was water. So it's minus n over r. So in this case, remember, the light is traveling from right to left, which means this surface is concave to the direction of propagation of the light. So it's negative value of that refractive index. So it becomes minus r. Oops. Sorry. So it becomes minus r.
Wait, so r is negative when it's convex or concave?
Concave.
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 Yeah. So in this problem, you can see, sorry. So in this problem, you can see I have drawn with this orange arrow the direction of propagation of the light.
Okay, right.
For this version. So this is for the part A. You'll see that in part B, because the question is reversed, the arrow will be opposite, and you will have the opposite sign for that. So that's it. I think this is all you have to be wary about. So usually the places where I also make mistakes and other students I've seen in the past make mistakes is they forget to write the matrices from output side to input side. So they reverse the order. That messes it up in the first place. And then you forget to put in the sign conventions or appropriately use the sign for the radius of curvature and so on. These are the two places where you can make mistakes. So I would be extra careful there. Otherwise, it's pretty straightforward. And then for the free space propagation inside water is the same thing, 1, 0, 1, and d over n becomes s prime over n, which is also equal to r, so r over n. And then I simply do the matrix multiplication for the last two matrices first, which becomes this. And you can also redo this in your own time and check. And then I do the matrix multiplication. So I did some simplification over here. And then I multiplied these two matrices again. And this is the final answer that I got, or the final version of the system matrix that I got. Now I go back to the question and see what else is asked. So it asks, where is Wanda's image formed? So firstly, it asks me a question related to the image, which means I should first identify what is the imaging condition. So now remember, in the summary slide here, the imaging condition is M21 equals 0. So I go back to my my system matrix, and this is my M21 term, right? M11, M12, M21, M22. So imaging condition says M21 terms equals 0. So S over n plus R over n equals 0, which means S equals minus R. And what does this tell us about the image? So where is the image formed? The image is formed at a distance R with a negative sign, right? Which means it's formed at the center of the ball. So it's negative R. And also the negative sign also tells me that it's a virtual image. These are the two inferences that we can draw from solving this equation. So that's the question asked. What is the image real or virtual? Because it's a negative sign, it's a virtual image. And where is it formed? It's at the center of the ball. And what else? Magnification. So magnification is pretty straightforward as well. So for lateral magnification, I again go back to the summary slide, and I see the lateral magnification is given by the M22 term. So I go back to my problem, and I see what is the M22 term, which is this one. And then from there, I do some basic, some simplification to find out what the magnification is. Then the next part of the problem asks the opposite version of this. So here the problem is reversed. So it asks, how does Olive look to Wanda, or how does the person look to the fish? So it's the exact opposite, which means the person is now the input and the fish is now the output. So the light ray travels from the left to right, which was kind of like the convention that we used to look at the examples in class. Again, I'll write from output side to input side, which means this part is first, like the free space propagation inside water is first, then refraction at spherical surface, and then free space propagation in air, multiplied by the input matrix, right? Again, I substitute n out equals n, because this is the output side in this case, and n in equals 1 because this is air, and rewrite this equation. I bring up the equation again over here. I refer to my free space propagation matrix and refraction at spherical surface matrix, and I plug them in here. Remember, so this is free space propagation inside water, so it's 1, 0, s prime over n, 1. Then refraction at spherical surface, so 1, 0. And here, because it's the same convention, and you can see because the light ray is traveling from left to right, the surface is convex, which means the radius of curvature retains the positive sign. So it's still r instead of minus r, which was in the last case. Then 1, 0, s, and 1, and the input matrix, right? So again, I do my simplifications for these, and this is the final version. So you can again check these by yourself, go over them once, make sure you don't make mistakes while doing the matrix multiplication, just to revise that. And again, I look at the imaging condition. So the imaging condition is m21 equals 0, which gives me that this equation equals 0. Now, for this case, there can be a few different cases that can arise when you have, so these were the steps that got me up till this equation, right? Which is here, this one. And so from that, we can derive some relation between s prime, which is the distance, which is the image distance, with respect to the object distance s and the radius of curvature of the sphere, water sphere. So now the lateral magnification is asked, and when you do the lateral magnification, you have a certain value, and the lateral magnification now we see will depend on what the values of s and r are. So there are two cases that you can go over. So in this case, in one situation, the image is virtual and erect, and in the other case, it's real and inverted. So it just depends if r is greater than s, or if r is greater than s times n minus 1, and so on, or the opposite case. I think, so in this case, the most important things to remember is you should refer to this slide for the imaging condition. Suppose you're asked what is the power of the optical system, then it would be minus m12. Lateral magnification, remember it's m22. I think the sign conventions slide is not in the midterm review slides, but it's in the geometrical optics main slide set. So remember, refer to the sign conventions and refer to what the translation through uniform medium and refraction by spherical surface matrices look like. So I think that should be the general way by which you can solve all kinds of problems related to geometric optics. There are a couple of more questions in problem set 2 here and here. They're solved exactly in the same way. But other than that, if you have any questions related, I can go over this, but do you have any questions in general to how to write the matrices or anything?
I have a quick question there. I'm so sorry. So there, whenever you're doing the matrix formulation, that case, I see it's a concave, but I think the way the resolution, it's positive R, so that got me confused there.
Sorry, can you say again?
Okay, Are you able to hear me?
Yeah.
Cool. Okay. So whenever I do the matrix formulation for this case, I can see it's a concave lens, okay?
Mm-hmm.
It would be a negative R, but I think on the resolution is a positive R. So I got confused on that problem.
So here, because what you're saying is the Plano concave lens, because this is generally the way in which we define this kind of lens, right? Now, in order to not, but we have to follow one kind of convention while solving the problems. You can always reverse conventions and solve the problems, you would get the same answer. But I would say just follow the conventions that we are going by in the class. So in class, what we defined was, first we identify which direction the light is traveling. And in this case, because this is the object, the light is traveling from left to right. And so if I draw an arrow going from here to from this direction to this direction. And when I do that, I see that this surface is convex to that light ray. I mean, yes, this is a Plano concave lens, that is correct. But this surface is basically just a spherical surface or a spherical interface between two media, one media being N and one media being air. And this surface is convex to the light ray, which is going from left to right. So if you follow that convention, then you can solve the problem correctly. So we just define this as a Plano concave lens. But when we are solving the problem, because we are following the sign conventions and exactly the way the sign conventions are defined, this plane becomes a convex lens to the light ray, which is traveling from left to right. Does that sort of answer your question?
Yeah.
Okay, let me try to bring up the slide for the sign conventions. So I think it's, yeah. So I would say just refer to this, that the radius of curvature is positive when the surface is convex towards the left. Now, this means that when the light ray is traveling from left to right, a surface which is curved like this is convex, and if it's curved the opposite way, it's concave. So I just look at this, and then I look at the problem that I have over here, and it exactly matches, right? So this is
okay, that makes sense. Yep.
Now, if it was if it was curved the other way, then you would have to use the opposite sign, the negative sign, basically. So
okay.
in this question, it says in the figure above, a point source shown by the red dot is located to the left of a Plano concave lens with a radius of its curved surface as r. The distance from the plane surface of the lens and the red dot is this, and the thickness is this. So where is the image of the red dot formed? Again, whenever a question related to image is formed, it means you have to immediately go to the imaging condition. Yeah, so the imaging condition. So remember, imaging condition M21 equals 0, which means you have to find out what M21 is, and that means you have to find out what the system matrix is, and that means you would have to make your matrix formulations, right? So let's see how this was solved. Again, same thing. Let me zoom in a little bit. So let us assume that there is formed a distance S prime. Let's assume that this is the distance, and then we will calculate what the distance is and so on, what the sign of the distance is and all that. So we write exactly the same way as I did this problem. So output side matrix equals this bunch of different matrices times the input side matrix, right? So output side matrix equals these different matrices times input side matrix. Now what I see is, again, I have to write from output side to input side. So what is the output side? The output side, let me assume that the output is somewhere here. I don't know what's going to happen. The final answer, the sign of the answer is going to tell me where the image would be formed. Let's assume for now, because the light rays are going from left to right, that the output is somewhere here. So then I write free space propagation in air, then refraction, then free space propagation inside the lens, refraction, free space propagation in air. So going from output to input. So let's see. So it's free space propagation in air over the distance S prime, which I said, let's assume the image distance is S prime. So that, then refraction at right concave surface of lens, then refraction at left plane surface of lens, and free space propagation in air, right? So I think, oh, okay. So it said the lens has a thickness of t equals 0. Okay, that's why I was like, where did this propagation inside the lens go? Okay, so it asked me to assume t equals 0. So basically that matrix vanishes. Otherwise, if the t is non-zero, then you would have to put in another propagation of the light ray inside the lens of finite thickness t in between these two refraction matrices. So other than that, we just plug in these values, and remember, because this is a plane surface, the radius of curvature is infinite. So this term would go to 0 basically, because there's like a large number in the denominator. So I do some simplifications, and again, for let's look at what happens to the refraction at the surfaces, like the question you asked. So the basic form of that matrix was 1, 0, 1, and then minus n out minus n in. So again, 1, 0, and 1, then minus. So refraction at right concave surface. What is the output side refractive index? 1. So 1 minus input side refractive index n. So n divided by light is going from left to right and the surface is convex. So positive r. So positive r, and that's it. So for the next one, it's the same thing, but the refractive indices get reversed because the output side is now the glass, the input side is air. So it becomes n minus 1. And the radius of curvature is a large number, let's say, tends to infinity. So this entire term becomes 0. So this becomes pretty easy to solve because these terms are all very easy to solve now, 1, 0, 0, 1, and so on. And I do all the matrix multiplications, and so I get my final system matrix, which is given over here. So the imaging condition is M21 equals 0. So this term equals 0, and so on. And then I do some simplifications, and I arrive at this kind of a solution, which is kind of similar to what the solution for the second part of the fish person problem was, right? Looks kind of same. And then that's basically my solution to where the image is formed. It's this value. Now, maybe in the midterm, you would be given certain values of S and R. Maybe you're asked like, okay, this is the radius of curvature of the lens, and this is the value of S, and so on. And then you'd be asked to find out a numerical form of the solution. So I would say instead of plugging in the numbers first, just plug in the numbers at the end, which makes life a lot easier, and then just compute what the numerical value of S prime is. Now, there are a few more questions. So it asks, where is the image of the red dot formed if S equals R? So that's also easy to solve now. In this equation, S prime equals this term. Just substitute S for R, and that brings it down to S prime equals minus R over N. Now it asks if R is like, this is one such example. So it now asks you if R equals 50 millimeters, and assume refractive index is that of glass. What is the value? So just simply replace R by 50 millimeters and N by 1.5, and so you get minus 33.33 millimeters. So that's the answer. So now it asks, is the image real or virtual? So the negative sign in the solution indicates that the image is virtual and is produced on the same side of the lens as where the red dot is, right?
Sorry,
So,
what does it mean by it being virtual?
So this is what it means by virtual image. So let's see. It basically means this is the object. So assume these are the rays going out from the object, right?
Yeah.
Now what happens is the rays suffer refraction at the first surface, go into the lens, suffer refraction again, and bend outward from the lens. If this surface was curved the other side, these rays would bend toward the optical axis and come to a point, which would be your image. In that case, the rays physically do meet up at this point on the optical surface, and that creates a real image. In this case, what happens is that the rays bend outward from the lens or whatever imaging system this is, and do not actually come to focus, come to form a real image. That's why it's called a virtual image. But what happens is, now if you look at, if you have your eye here and you're looking at the rays, your eye traces the rays backward through the optical system to form an image which is called the virtual image. It's called a virtual image because the rays are not physically going to a point. They are not physically coming to a collection at a point. They are going outward, but your eye traces them backward to form a virtual image.
Okay.
This is how a magnifying glass works. Basically, you have an object and you put your magnifying glass very close to the object, and the virtual image looks bigger than the actual object was. So that's
like with a real image, if you had like a wall there, then the image would actually like be on the wall, right?
That is correct. Yeah.
Okay.
So and also in that case, you would have to curve the surface the other way, because you can see physically the way the surfaces are set up, that the final rays which exit from the system are always going to go away from each other, or rather away from the optical axis, which means they would never converge to a point on the optical axis. But if you want to form a real image, that means that you have to curve it the other way, and then you can form the real image on the optical axis.
Okay, cool.
Okay. Yeah, so that's the explanation. And it asks, what is the magnification? So I think there is a question, what is the lateral magnification? So lateral magnification is very simple. It's given by M22, again, refer to summary slide, and plug in whatever is M22 over here from the system matrix. M22 is this, right? And then I plugged in the values. I calculated S prime from here, and N equals 1.5 and so on. So I see the image is demagnified because it's less than 1. So if it was greater than 1, it would work, it would be like a magnifying glass. So it would get blown up. It's 2.5 times the object size. It gets blown up. It can be less than 1, which means it's a virtual image, but it's demagnified. It becomes smaller than the object, which is fine. Whatever it is, that's the solution. So I think that's for this kind of problem. Do you think you guys can go back and maybe work this out step by step by yourself, or do you want me to provide these kind of slides for this problem as well?
Are you saying the mathematic part of matrix multiplication? Is that what you're saying, or?
No, because in this slide I don't show the steps. Well, the steps are shown, but you will have to do the matrix multiplications by hand, right? But I'm saying, like, here how I do this step by step, like I identify what the output is, what the input is, then I write all these step by step. Do you need them for this, or can you follow along with these slides for this one problem and translate over to this problem, because it's solved the exact same way? I think it's okay, right? I mean,
yeah, it shouldn't be that hard. It's pretty. We can follow along this problem at least.
I mean, all of the matrix related problems are going to be solved the exact same. So only maybe the surface is curved the other side, or there's so many different combinations that I can come up with anyways when thinking of problems. So maybe you'll have a different curvature on one side, or some distance will be different, or maybe you will have a non-zero thickness and so on. So you'd have to factor in a matrix over here. But the idea by which all the steps remain the same. You basically write your output side matrix equals multiplications of different matrices times your input side matrix, and then you refer to the forms of the free space propagation matrix, refraction at spherical surface matrix, and write those down. Remember to go from output to input, and then matrix multiplication is up to you that you don't make a mistake and do the correct multiplication and solve the problem. Okay, so I think this is another question that we have. So geometric optics related question, yeah. So this says it's a biconvex lens which has a focal length of 100 millimeters. An elongated object in the shape of an arrow is placed at a distance of 150 millimeters away from the lens. So let's see. It's like this case, or either of the cases. So basically you have a biconvex lens, both sides are convex. There is an object which is placed at a certain distance away from the lens, which is S. The lens will have a focal length given by F, and we assume an image is formed S prime distance away from the lens. Now, depending on where you place the object, this S prime and the image type will change, and that's what this problem is asking us. So for this part, we refer to these slides again. So this is the thin lens with biconvex lens and so on, and also there's let's see, this equation, yeah. So slide 44. So the system immersed in air that we solved, which gave us this equation 1 over object distance plus 1 over image distance equals 1 over f. So we'll make use of this problem. We'll make use of this equation over here. How do we do that? So we know from imaging condition that 1 over s plus 1 over s prime equals 1 over f, right? So that's here. Yeah, 1 over s plus 1 over s prime equals 1 over f. The imaging condition is obviously satisfied because the biconvex lens is forming an image. So here the S is the object distance, S prime is the image distance, and F is the focal length of the imaging system, which are all given. So it asks, where is the image formed? This is very straightforward. So I'll just replace S, object distance, by the distance 150 millimeters, where it says the arrow is placed away from the lens. So that's my object distance, 1 over 150, plus 1 over S prime equals 1 over 100, which is the focal length of the lens, right? And so if I solve all that, I get S prime equals 300. So in this problem, S prime is 300. So this was 150, and the image is formed twice that distance away from the lens. This is positive sign, so it's formed on the other side of the lens. It's a real image and inverted. So then the question is, what is the lateral magnification of the image? The lateral magnification of the image is given by S prime over S. There is a typo over here. This S is 150, not 100. I'll correct this and post another version. I'll just make a note that I made a mistake, like the focal length was 100 and the distance was 150. I messed it up here. So it's S equals 150. So the lateral magnification will be 2, and the image would be magnified by 2x then. Okay, next is the image real or virtual? Since the image distance is greater than 0, hence the image is real and inverted. And how would this situation change? Is the object distance becomes equal to 75 millimeters. So you make use of the same equation, 1 over 75 plus 1 over S prime equals 1 over 100, and solve it accordingly. And what we get is S prime equals minus 300. So now you see that the image is formed on the other side because of the negative sign. And the lateral magnification, again, this would be 150, not 100, would be minus 2. So it would be again magnified by 2x, but it's a virtual image. So what basically happened, you see the lens had a focal length of 100
I'm
millimeters.
sorry, isn't it 75 in this case?
Yeah, sorry, 75, yeah.
Okay.
Don't know why I keep making this noise. Yeah, so yeah, the object distance is 75, yeah. So that would be 4 times. And so the question is, yeah, so what happens exactly physically? So the focal length of the lens is 100 millimeters, right? So this doesn't change, the F doesn't change. And the F is also same on the other side, right? So this is F I have drawn over here, but I can also draw an F distance on this side, on the left side of the lens. So you see what we did was we first placed the object at a distance which was greater than the focal length of the lens, And then in the second case, we brought the object closer to the lens so that the distance it was away from the lens was smaller than the focal length of the lens. And immediately the rays that can be traced changed their directions, because you can see I've just drawn the principal rays, right? One ray going parallel to the optical axis, which then goes through the focus of the lens. One ray which goes through the center of the lens, which means that it cannot suffer any refraction, right? And meets at a point. And one ray which goes parallel to the optical axis. And that's how I drew my image. Now simply, just by hand, I moved this object closer and tried to draw the same rays. So this ray, which goes parallel to the optical axis, goes through the focus, right? Is here. I draw one more straight ray which goes through the center of the lens here, and one ray parallel. So you see these rays cannot physically meet up like they did in the first case. So if you place your eye over here and look at the rays like I showed in the case of a virtual image, because the rays are not going to physically converge at a point, your eye is going to trace out the virtual rays meeting at a point, and that is where the virtual image will be formed of this lens. This is exactly how a magnifying glass works. So if you take the magnifying glass closer and further away from the object that you're trying to magnify, you will see that up till a certain distance, when it is close to the object, you will see the image is not inverted, it's erect and it's magnified. But then if you bring it further away from the object, it's going to blow up out of proportion and then flip, because then it would become this kind of a case and it would form a real image. So this is some experiment which can be done very easily using magnifying glass. Just by changing the distance of the object from the lens, by once keeping it further away from its focal length and once keeping it inside the focal length, right? You can get magnifications in both cases, right? So this time also the image was bigger than the object. It was two times bigger, and this time it becomes 4 times. But one is real and inverted because that's how you can trace the rays, and the other case it's virtual and erect.
So if it's real, is it always going to be inverted?
If it's real, it's always going to be inverted, yes.
Okay, cool. Thank you.
And I think the best way to judge that is if you just draw out the diagram by your hand, you'll see that there is only one way you can draw this, right? If you keep placing the object further and further away and keep trying to draw the diagram, you'll see the size of the image will change, but the orientation of the image will not change. Right. And this is true for all these kind of biconvex lenses, like the human eye is a biconvex lens, and it creates an inverted image of the real world that it's looking at on the retina. That's actually true. And then your brain takes inputs from other sense organs like your ears and so on, which tells us which way is up and so on. And then it reverses the image which is formed on the retina and gives us the right side view of the world. But because the human lens is also a biconvex lens, the image formed on the retina is always inverted. Same for camera lenses. Your phone camera or DSLR, all the images are always inverted. Then there's a software inside the phone or the camera which basically flips the image and shows it to us right side up. But if you were to place a piece of paper in front of the sensor, so imagine this is your outside world, this is a lens, and here is your sensor forming the image or capturing the image. If you place a piece of paper, you'll see that the image is upside down. So that's always true in this case. And this is kind of like the case for the magnifying glass. Okay. I think. Okay, any questions? Any more questions from all this? Other than that, I think this year we did not cover the prisms. So in the midterm, that won't be there. I forget if, so I don't know if Dr. Menon covered these concentrators in class. Dr. Menon?
Yeah, I did, yeah. So if there are any questions, we can address them, but I think pretty Reasonable.
So there would be just these, right? Just these slides. But so the prisms and the prism slides are not in the midterm because we didn't get a chance to talk about those. Okay. Oh yes, so there's one more thing. There's this other problem in the set 1.
Yeah,
This
the
microscope
telescope, the microscope. Yeah, that's
so there's one thing here. So this part B, don't worry about this because this has to do with the how the human eye works, and that's also something that was not covered. So part B, don't worry about it. It's not going to be there. Just part A, and part A is again pretty straightforward, right? So you have an object distance and focal length of the lens and image distance, and it asks you where should the object distance be formed? Where should the object be placed? So this is the reverse of this question, where all the questions asked are about the image, where is the image formed, and so on. In this case, it asks you where should the object be placed so that the image distance is this, and just plug it into the same equation and find out this should be the object distance. Yeah, and that's it. Just remember these other small formula in the other slides, that there are the energy equation, how it's related to the wavelength and of the light, and so on.
Sorry, really quickly, how does that stop affect it in that problem that you just looked at?
Here, this one?
Yeah.
So basically what this is how this works is, see, this is the object, right? So if maybe I'll actually provide a slide that Dr. Menon can upload where I'll show, like, if you draw the arrows going from the object, you'll see that they form an image over here. Now this is how a microscope works. Basically you have this tiny object that you're trying to magnify and then view with your eye, right? So the microscope has two lenses. One is this magnifying lens and one is the eyepiece. The function of the eyepiece is to collect the rays formed by the image and make them into parallel rays, which your eye can then view properly. So the image formed is at this plane. And then if you draw out the rays again, then you'll see that the rays from the image go into this lens, and then they become parallel rays which go to the eyes, right? Now the stop basically means that you can, if you use an iris sort of a thing, or an aperture, which is the cross section of a circular aperture is basically like this, right? So it's like a stop. So you limit the size of the object. That's all that the stop does. If you make it bigger or smaller, you basically make it like a field stop, so you can limit how much of the image you see. All this, the function of the stop in this problem is to basically tell you this is where the image is being formed.
Right. So that second lens doesn't really matter then for that.
It doesn't really, yeah. So that you understand that 170 millimeters in this case is what the image distance is, and you can plug it in here.
Right. Okay.
See, because it says the first lens L1 forms an intermediate image at the S2 plane. That's all why S2 is there.
I see. Cool. Thank you.
Just one quick question here, just as like to, stick in the head this idea. So you're saying about real image is always going to be inverted.
Mm-hmm.
That being said, I'm thinking that virtual image is always going to be erect. And this is always like that?
Yes, that's true.
Okay, just to have this idea. And the lateral magnification, of course, if you have greater than one, we're magnifying it. And if you have less than one, of course, we're demagnifying. So we can like memorize this pretty much, right?
Yeah, I mean, it's
conceptual.
Yeah, and it's common sense, because the magnification is straightforward common sense, because if it's less than one, obviously the image is smaller, right? And the other way, I would say, instead of memorizing anything, just remember this diagram.
Okay.
Or if you are sometimes asked how, you can just draw this even by hand and figure out what is going to happen to the image, right?
Thank you.
Yeah. Okay. I think that's it from my side. If you guys have any more questions, otherwise, if Dr. Menon wants to add anything from the concentrators, because I think I skipped those classes this year. So.
No, I think this is good. So let's give a few minutes if there are any questions the students want us to address.
And I think I was a little bit busy last week, so but I'll be on Slack today and tomorrow up till the midterm. So if you have any questions, I'd be prompt to respond to those.
Yeah, so my main advice would be to make sure you work out the examples yourself. Or you know, with your fellow students. You can collaborate when you study. This is perfectly fine, but just make sure you're able to do it. You understand how to do it. Okay, I guess no questions.
Yeah, do you have any questions from the concentrators? This is also pretty straightforward as far as I remember from doing the class earlier, that this slide is like the important slide, which gives you the relation between the two heights. And there's I think this one, between the two apertures, that it's related by the sine of the angle.
Yes, you should be able to design the CPCs. I mean,
yeah.
Are there any like practice concentrator problems we can work on?
I think there were a couple in the lecture slides themselves.
Okay.
But otherwise, I don't think we have any extra.
Yeah.
I don't remember, but
I think it's because there's only kind of like one question that can be asked from this. So it would be basically like maybe using something like this equation. Right? So there's not much to.
Okay. Yeah. I would say the only other thing is after the midterm, make sure you start spending some time on the next assignment, because that is due 2 weeks after. So please keep that in mind. Yeah, that's it. And you know, if you have any questions, of course, post on Slack or email. Again, the exam will be posted on Canvas, probably as an announcement. So just, and I assume when we post an announcement, everyone gets an email. Now, if you don't have it by Thursday, 9 a.m., make sure you let me know.
Okay. And then I just had a question in regards to some of the topics, topic lectures that we reviewed, the anti-reflection coding, thermodynamics, and then the statistical ray optics. Those will be fair game for the midterms as well, correct?
I would say the statistical ray optics probably not. So
okay.
feel free to prioritize it lower, because it's a little abstract and we went through it a little fast. But things like anti-reflection codings are relatively straightforward. And in thermodynamics, again, just the very basic concepts. You know, you can imagine things like the Stefan-Boltzmann law, right? So you understand how radiation losses change with temperature. But I don't expect you to understand or ask any detailed questions about heat engines, for instance, because this is not a thermodynamics class.
Okay.
Yeah, so many of those lectures are really, I want you to recognize where, I mean, optics is only one part of the puzzle, right? I mean, there's many other things that go into actually solving particular problems. And I want you to be aware of what the other things are and how everything fits together. And keep in mind, the midterm is what, 15% or 20% of the grade? So yeah, I mean, I would also add that historically, most students do pretty poorly on the midterm, but we've never done it at home like this because of COVID. Usually it happens in person.
Actually, last year they did pretty well.
Okay, okay, last year was an anomaly, so maybe it's okay. So don't feel so bad if you don't do great. But, you know, again, the goal is not to penalize you, but for you to make sure you understand what we have talked about for half of the semester, right? You don't want to waste your time, so.
And
Okay.
I
Yeah.
assume you would post today's lecture, this exam.
Yes, yes, yeah.
Later on the
Yeah.
website page or Canvas.
Yes, yes, both. Yeah, in a few hours. Yeah.
Thank you.
Okay,
I think
perfect.
this set you already posted, right? The.
Yeah, yeah. I'm just saying this recording.
Oh,
This-
okay.
this, yeah, Zoom recording. Okay, perfect. So, well, good luck. And again, remember Thursday, there is no class. So take a break, enjoy the nice weather. Okay, everyone, take care.
Thank you very much.
See you all next week.
Thank you.
Thank you.
Bye-bye.
Bye.